I would say the best of the best in this field, the CPP field, are here. Why not come here, meet them, learn from them, do it in person, as we know that's a lot better than getting to do things virtually. So where else can you come somewhere where all the experts are?
Hello, everyone. My name is Katherine Rocha, and today we're going to be talking about some design trends. And we're going to be looking at legacy design trends and then the current design trends that have replaced them and kind of try and figure out, is the newer thing better or is the older thing better? Cool. So here's just a little bit about me. I'm a software engineer at Atomos Space. It's a really small startup in Broomfield, Colorado. And I'm currently working on a 4-year-old code base, and it's running C++23, which is super cool for space and super unique. And it also only has around 100,000 lines of code. So very small. We're able to make a lot more changes that you aren't able to typically make in these really massive legacy code bases. However, I previously worked in a 20-plus-year-old code base that was running modern C++. However, because it had existed for 20-plus years, you still had macros and all the other things that made it really difficult in order to actually revolutionize and write new code. So you still had all those issues of things have been done for so long, and so how do we change things? And this is kind of what inspired this talk, is figuring out, we've written all these things and we have all this legacy code. How do we end up moving forward, and how do we end up writing new code? And is the newer thing better or is the older thing better? And I'm kind of a self-proclaimed software historian or genealogist. If you've seen any of my other talks, I tend to focus on how we can write code better and how we can understand why we're doing the things that we're doing. Cool. So as I said, I work at a small company called Atomos Space. We work on orbital transfer vehicles. So these are spacecraft that attach to other spacecraft and move them around in space. So we can relocate a spacecraft to where it needs to be, allowing it to extend its life so we don't have to send up a new spacecraft, which is a really cool mission. So if this is something that you end up becoming interested in, we do have some positions coming up in the future. Cool. So I was really interested in trying to understand the past, understand why we're doing the things that we're doing, and investigating these new patterns with the same scrutiny as the old. I noticed that we tend to have two camps of people. We have the people who have been working in industry for forever, have been using these design patterns for forever, and they're convinced that just because we've done it for years, this is the way we need to keep doing it. And then you have your software engineer that just graduated college, comes in, has all these bright new ideas, and they end up telling you, hey, we should do it this way because I saw it this way and this looks really cool. And both of those end up clashing a lot, and you end up usually having the senior engineer say, well, we've done it this way, and this is what I'm used to, and this is what the code base does, and so this is what we should keep doing. And so we need to figure out kind of a middle ground and understand both perspectives in order to be able to make the best decision for our code bases, while still incorporating some of that legacy and still trying to keep consistency across our entire code base. Cool. And this is one of these things that we don't just see in software, we also see in real life. You look at things like water bottles. A few years ago, everybody had a Hydro Flask water bottle, and that was the cool thing, and you had to go out and buy your own. And now that's not the cool new water bottle. And if you're using that, it's like, should I keep using the old water bottle that's still functional, or should I upgrade to this new water bottle just because it's new? And that's something that we don't quite have the answer for in the rest of life, but maybe we can analyze and figure out a better way to do it in software engineering. Cool. So here's kind of the process we're going to go through to figure out how we're going to, what these design trends have going for us. So first, we're going to look at a timeline. We're going to kind of look at the original, look at the new, see kind of when each of these things happened. And then we're going to look at the original trend and try and understand why was it used and what was it. And then we're going to do the same for the new trend, while also looking at why did we replace it and why are we not, or why did we replace the original and why are we not using it anymore? And then we're going to also look at the source code for each and try and understand how elegant is it, what are the problems with it, what makes us happy about this code and what doesn't make us happy about this code when we're doing a code review. And with this is all code that I've written, and the idea is it's not perfect. The idea is that we can talk about it as a group and do a little bit of a code review and understand what's good and what's bad about this code, because I don't have all the answers and neither do all of us. And so if we all pull our mindsets together, we'll end up coming up with an answer that works for everybody, and then we'll end up knowing a little bit more about some of these patterns. And then we're going to kind of do a little bit of analysis and understand what's good and what's bad about each of these trends. Cool. So this is going to be a little bit interactive, and we'll see how it goes as we go along. Cool. So our first one we're going to do is going to be really easy, really quick, just kind of do a little bit of research and look at how we're going to be doing this for the future. Our first is the index for loop versus a range-based for loop. Now, who here uses range-based for loops on a regular basis? Okay, most of the hands went up. Awesome. Cool. So we have our index for loop, and then range-based for loops came into effect in C++11. Cool. So the cool thing about our index for loops is we have an index that can be used to access an individual element, and we can also use that index for other side effects. The idea being that this index isn't just for accessing the element, but we can do whatever we want with it. If we want to use that number for another calculation or do something else, we can do that. It also doesn't really require a group of items. However, the access operations can be a little bit more dangerous. So here's an example of the code. If you notice, there are two different ways that we can access each of those elements. You can access it via the braces with the index inside of it, or you can use .at. And one of those will throw an exception, and the other one, if you send in an invalid index, you're going to have a lot of issues. And so these are both cases that you may not want in your code or may not be able to deal with, because some code you don't really want to throw an exception because you know what's going to happen in this function and you don't want it to happen. And some code, you don't want to accept the risk that there may be an issue. And so this can lead to a lot of issues and cause problems with all these other side effects. Cool. And then here's our new trend, which is the range-based for loop. This tends to be a little bit more data-oriented, and it's also a lot more readable. So you look at a range-based for loop and you're like, I know exactly what we're doing, I know what we're looking into. And so if you notice on the top line, we have our different objects that are in space. We have our sun, our Earth, our moon, and Jupiter, and then we can say, okay, well, we're pulling an object out of this vector, and then we're going to output our object. And this is really nice because we can visually see what we're doing and kind of understand what's going on, and it's a lot more readable, and we aren't worried about that index being used for anything else, because we don't actually have access to it. Cool. So here's kind of our comparison. As you can see for the index for loop, we can add a lot of these side effects, which are really great for doing math operations. However, it can be difficult to have some of these complicated checks and understand exactly what's going on, because when you look at it visually, you actually have to look at the loop and see what's going on and make sure that we are doing our indices correctly. And then for range-based for loops, they're really easy to read, really easy to access, but if I'm trying to do something sneaky with some side effects, I'm going to run into some problems. Although if you are running into issues where you're trying to do things with side effects, maybe you need to do a re-architecture to avoid having that happen. Cool. So that's a little preview into kind of what we're going to be doing to walk through all these different examples and understand what are the pros and cons of each of these design patterns. So we're going to start with the old one, kind of do a little analysis, and then move on to the new one. Cool. So up next is kind of our globals that we have to deal with in our code base. And unfortunately, a lot of code has globals that we need to deal with in some way, shape, or form. So we have our global interface and our global data. Also, if there are any questions or anyone has anything, feel free to raise your hand or add it in while we're going along. Cool. So we have our global interface and our global data. Our global interfaces are things like external I/O, things we're trying to access and we only want one copy of that we're going to reach out for. And then we have global data, and these are things like our parameters. So a good example, since I work in space, is we have our X, Y, and Z, or our position, velocity, and acceleration. These are things that may be passed around across the entire software stack of the current position, but we may only have 2 people updating it. So we want everyone to be able to access these parameters, but only a couple people to be able to write to those parameters, and we want to make sure everyone has the most updated data. Cool. So here's kind of our timeline of how we dealt with it. We have our traditional global variables that get passed around everywhere, and then we have our Gang of 4 design pattern singleton, which is the Gang of 4 book is a book that was really revolutionary and was one of the original books talking about design patterns and some of these things that we can do for object-oriented programming. And then we transition into the Myers singleton, and then we're going to look at monostate and then dependency injection. Cool. So our original trend is singleton. The idea being we're going to hold all of our global data in one copy and everyone can access it. Who here has used a singleton? Cool. This is most of the room. Who here likes using singletons? There's a couple. Okay. Who here would be willing to write a singleton in their code today? Okay. About the same couple raise their hand again. So what's nice about a singleton is you access your code via a get instance or an instance function. So this is really recognizable because as I'm going through my code base, I'm going to look through and I'm going to see an instance function. I'm going to go, oh, we're looking at a singleton here. And that's really recognizable for anyone working in their code. And that makes it really identifiable. However, it can be really hard to test, and it can be really hard to understand everything that's going on. And you have testing, and you're accessing this global interface, and it's hard to pull that out. And so as we're testing, you may have those issues like having to open up a database in order to test our code. And then when you look at your older software, it becomes quintessentially overused of, why don't we just put all this data into a singleton and then pass it around everywhere? And this has kind of transitioned as we've gotten more recently. As you can tell by the hands in the room who would continue to write a singleton, you aren't writing singletons today, so they don't tend to be added into the code base as much anymore. Cool. So here are two different singletons. I'm going to give you all a second to take a look at them and figure out kind of what you like, what you don't like about it. So they're both for plotting. The idea being, wanted to choose something that wasn't logging, as that's your traditional example. And basically we have a plotter, and we can assume that there's some underlying data structure that we're trying to, or underlying external data that we're trying to access with our plotter. And so we have two different singletons that we're using in order to in order to send data to that external interface. Cool. So the first one is the design pattern singleton on the left. And this is one that you can notice is an older style pattern. This is taken pretty much from the Gang of Four's book. You can tell that by the null in the actual thing. We aren't using null pointer, we're writing older C++ than that. And then you can also tell the instance, we do have a potential for a race condition, and we also don't have the code ending up being cleaned up afterwards. We're gonna hope that when the program terminates, everything's gonna hopefully get cleaned up by the OS, because we aren't actually cleaning that code up as we finish. And then we have our Myers singleton, which does a better job of cleanup, and also is being really creative with using that static variable, and so you aren't having as many potential race conditions. Cool. So then now, when you've started liking using a singleton, you want to make it easy for other people to write singletons. And one of the big things with singletons is as people write them, they tend to write them a little bit differently every time you write a singleton. And so one solution is to wrap it in a template. And so what we're going to do is we're going to make a template that can hold the instance. And so, or a template that's templatized on the type. And so then our get instance is always the same. And then we're just going to use a using statement and create our plotting singleton that way. Cool. So has anyone done this in their current code base or seen this? Yeah, okay, there's a couple of hands. Cool. So this is really nice because it allows us to actually look at actually create these singletons consistently every single time and not have to worry about someone referencing a different area and writing it a little bit differently. Cool. Next up is monostate. Who here has written or used a monostate or knows what a monostate is? Okay, there's a couple. It's definitely a less common design pattern. Basically, instead of having this global class that everyone accesses, we take the class and we move all of the objects in the class and make them all static. So we have one copy of every single thing inside the class, but multiple class copies. And this is really easy to transition to that multiple object model while still having the ability to access a single, still having that global data. However, it can't really replace those interface instances a lot of times because you do have that external I/O that we're trying to access, and you can have kind of complicated patterns to access that external I/O. So with this, instead of having our external I/O, we're gonna have a queue that we're updating every time, and that's marked static. So does this feel better or worse than the singletons before? Like thumbs up, thumbs down? Okay. We're getting a lot of thumbs down. Yeah. So as you notice, it is hiding that state. So now we don't know if we're accessing it externally, we don't see that get instance anymore. We don't know we're operating on something that does have these things being shared everywhere. Cool. And then our new trend, which is dependency injection. So the idea being we aren't having a global object anymore, and we're gonna inject the dependency into each of our using objects. So everyone who's using the dependency, we're gonna inject the dependency in. Now, when I was working on writing this talk, I got really confused about the difference between dependency injection and dependency inversion principle. They both start with dependency, and inversion and injection sound really similar. And then this is made worse by we actually end up using one to do the other. So dependency inversion principle, basically we're eliminating our dependency by adding in an interface class. So basically if we want to use our plotter and have a live plotter, we can access it that way, but we can also have a mocked out plotter that doesn't actually interact with a bunch of the I/O for unit tests, for example. And it reduces some of the volatility due to your implementation because we're no longer implementing things and having to deal with we aren't having to deal with the implementation changing because it's in live plotter. So as long as we aren't changing the plotter interface, it makes it a little bit easier to isolate out and make sure our tests and things aren't changing behavior-wise across our entire code. Cool. And then dependency injection. So basically you're gonna inject into the dependency into the object, and there's 3 ways you can do that. The first one is interface or template parameter injection. The second one is setter injection, and the third is constructor. And the idea is that we're sharing our object across all of these, into another object, and so we're gonna pass it around. And there are different ways we can pass it around and different ways we can limit the impact of passing it around and kind of do creative things to make it a little less obvious to the user that we're passing around all these parameters in. So here's an example, and it may seem like we're passing it in 3 different ways and this is really redundant, but the idea instead is we're gonna pass it around and we're gonna pass it in these 3 different ways, and you'd probably only use one of the 3. And then the ampersand needs to be moved to the other side, the left side, not the right side. So basically, on your constructor, if you wanted to use your constructor to inject your dependency, you're gonna send it in that way. If you wanted to use a setter, you can send it in that way. And then probably the best is to use inside of your get position, velocity acceleration, we're gonna call and send that in, so that way we aren't holding on to that dependency and we're only using it when we need it. However, this can be really difficult when we have something like a logger that's getting passed around everywhere and exists throughout our entire code base. It also runs into some interesting lifetime issues if you're holding a reference to an object throughout your entire lifetime. So there's some things we can do to eliminate it and make it a little bit cleaner. I would recommend looking when it comes onto YouTube at Pete Muldoon's talk about dependency injection that happened earlier this week. And he had some tips and tricks to make this a lot easier and make it look a little bit cleaner as well. Cool. So here's kind of a comparison of everything. So with the singleton, it's really easy to recognize, it's easy to access. You look at a singleton and everyone knows it's a singleton and everyone knows how to use it. And then with the monostate, it's really non-intuitive. And as we saw from everyone, it's not super well known. So if we're using it, there's a chance that the other developers on the team don't actually know what the monostate is and will make assumptions that it's acting like an ordinary class and potentially run into a lot of surprising issues. And then it can be really easy to transfer to individual objects as well, because we do have that shared inside of the class. So if we're able to isolate out that sharing and get rid of those statics, we're able to just make it so that way we're sending around the copies of that class. And then maybe it's less powerful than the singleton, since we aren't able to deal with some of those interface globals as much anymore either. And then we have dependency injection, and it's really nice because the access is really explicit and it's also really visual. However, you can end up having issues where you're packing multiple things in, and that can make it really hard to read and really hard to understand. Cool. So now we're gonna go to Spinning and concepts. So with that, as we're going in, we're gonna see kind of where everyone's working C++ version-wise. So who all's working in a C++ 11 code base? Okay, we got a couple of hands. Or maybe who's working in a code base C++ 11 or older than C++ 11? Okay, there's a couple. And then C++ 14, there's a couple. 17, okay. There's a decent chunk here. And then who's in 20? Okay, there's a little bit less than 17. And then who's in 23? Okay, there's like, you can count it on one hand, how many are in 23? Cool. So concepts came in C++ 20, so a lot of people won't actually have access to that feature. So kind of the idea is that we want to add requirements to our functions, and we want to make it so that way everybody is able to, so that way we write a function and then it makes it really clear, okay, I'm trying to use this function, what are the requirements for the function, and eliminating some potential errors so that way we can break sooner in compile time and have our compile time errors be a little bit easier to read. Cool. So with this, we're going to use run a cut of 4, which is it's a numerical approximation for nonlinear equations. Basically what's going on here is we have our time and then our initial value and a time step, and we're gonna use that to project into the future and get a potential future value. And so with that, we're gonna have these states, and we're gonna use that in order to project forward and figure out what's going on. And as you notice here, I've done some creative things that aren't gonna be the most helpful as we move to templatizing. Yeah, so first we're gonna start with our initial implementation, and this is great. We're taking in a double, okay. Yeah, we're taking in 2 doubles, and it's awesome, and it works, and everything's great. However, then we're gonna decide that instead we're gonna wanna send in an eigenmatrix and get a little bit of additional information out. Now this works, but now I have to start changing my class in order to deal with these additional things and making additional copies of my class. And this starts to become where templates can be really nice in order to genericize my code. And so this works, and this is great. And so now we're gonna make it into a template, and we're gonna templatize on the time and the output type, because maybe time we don't wanna have in int or something. Maybe we're wanting to use like a UNT because it's a super small time value, and we're using it from a telemetrized packet, and so it has to be in this really weird, obscure data type. And so we want to have that kind of flexibility to move across all these different things. Cool. Yeah. And then, so then I say, okay, I want to put a string in there, and we're going to run into some errors, because suddenly we have it, if you look at our code, we have, okay, so time is going to end up being added to a time step, and then time step is also time, and so it also needs to be multiplied by this constant 0.5. And so if those 2 operations don't work, we're gonna run into some issues. And then output type has to be able to be added to, output type has to be able to be added to another output type. And so these are kind of our constraints that we have on the system in order to ensure that everything's gonna mathematically work together. And if those don't work, we're gonna start running into compiler errors. And so when we send a string in, we're gonna have some compiler errors because we can add 2 strings together, but we can't multiply a string by 0.5. Cool. And so we're gonna get this out if we don't have any compiler, if we don't have any spin-A or concepts. Cool. I'm gonna give you all a second to try and figure out what's going on here. Who would consider this the like cleanest, most beautiful error they've ever seen? Okay, like no one. This is one of those where I would end up going, taking a break, leaving for a little bit, and then coming back, and then taking a look at it again, and then being like, okay, we're gonna start parsing line by line and figuring out kind of what's going on. It does have the hints that I need to figure out what's going on, but it's not handing it to me nicely. Cool. So here's kind of our timeline. So around 2002, spin-A got created. And then at C++11, we got type traits, which made spin-A even stronger and allowed us to do a lot more. And then we got concepts in C++20. So spin-A stands for substitution failure is not an error. Basically, it's a way to constrain templates, and it's kind of known for difficult to read errors, and it can be really difficult to constrain. It's also one of those that's really difficult to figure out how to use. So while I was trying to figure out this talk and trying to look into how to use spin-A, there's a lot of resources on it, but it's kind of confusing, and a lot of the documentation ends up being kind of hearsay. So if you talk to someone who writes a lot of spin-A, they know how to do it, and they'll tell you all the tips and tricks about how to write spin-A, but if you don't know that, you aren't going to be able to write it on your own. And so we kind of have to parse through it that way in order to understand what's going on. Cool. So here's our spin-A, and as we're parsing through, we have our enable if, and that allows us to, so we're going to enable if is arithmetic v time. So if time is an arithmetic type, then we'll enable the concept or enable the template. And so with the is arithmetic v, that's checking if we can, that's checking if it's an int or it's checking if it's an int or that category, and then it's also checking if it's like a floating point number. And so those are the 2 things that it's checking for. However, we also want to constrain output type. And that one's where it gets a little bit harder. And I tried to do it myself, however, it can get really complicated really quickly and can be really difficult for you to figure out how to constrain and figure out how to work through. And so with that, I ended up needing to pull on Boost and pull in the Boost libraries in order to figure out how to constrain that. And so I used boost, has multiplies, and has plus. And that allowed me to kind of constrain it. And if you notice here, I did 2 of them. And so the 2 are there because that way I could more easily read and understand in my code, okay, the first one is checking if it's an arithmetic value on time, and then the second one is constraining that output type. So that way I can know, okay, output type is something that has a multiply, a plus, or is an arithmetic type. Trying to make it really easy for us to understand what's going on and read our code later. Because that's really what's important, is less about like maybe some of the other things going on, but we want our future selves to be able to read and understand what's going on and how to write the code. Cool. And then just an interesting thing to note, we do the bool equals true at the end, and that allows us to, and that makes it so that way we're able to do more deductions. Cool. So here's our compiler error output for sending that string in. I'll give everyone a minute to take a look through it and see if it's a little bit better to read. Cool. So who thinks this is a lot better to read? Can I get like a thumbs up, thumbs down on who's happy about this code? Okay, we're getting some like of varying levels. Okay, so as I'm reading it, I'm gonna start looking through and it'll kind of make sense. And as I'm working my way through, I'll see things like, in here it has, where is it? One sec. Yeah, it does say it's not satisfied, which is really helpful, but it also says boost binary op detail, don't care, : value. And it has all this interesting stuff where it's like, well, what am I actually reading? And because we're dealing with some of the boost libraries, you're starting to get some more of the template interestingness that makes it a little bit harder to read and understand, which is something that if you've used any part of boost and done anything wrong and not looked at the documentation, you'll end up kind of getting a stream of errors, and that can be really difficult to understand and parse through just because of those templatized types. And so our goal is to make this a little bit easier to read and a little bit easier to work through. Cool. So now we're going to use concepts. Concepts were introduced in C++20, and the idea being it's a compile time constraint and a named set of requirements. So this will improve your compiler errors and make it a lot easier to create constraints for, and make it so that way everything will work together a little bit nicer, hopefully. Now, who here's actually used concepts? Okay, we're getting a decent chunk of hands in the room. Who here likes using concepts after using it the first time and continues to use concepts? Okay, pretty much the same hands are up in the room. So concepts are something that have kind of revolutionized how we're writing templates and how we're ending up constraining our templates and understanding what's going on. Cool. So with our concepts, first we're going to deal with that arithmetic type. And interestingly enough, there isn't a stood arithmetic. However, we could pull back on the type traits in order to bring that in. But in this case, I did the integral or floating point here. And then instead, I just said template arithmetic time. And so that says, okay, well, this is an arithmetic type, and this is how we're going to access it. Cool. And so now this is constrained, so that way time is going to be an arithmetic type. Okay. So now we're going to do our other constraint. And our other constraint for our output type is that we need to be able to add and multiply. Those are the two things that we need to be able to do in order to actually compute our next value. And so we have two constraints that our type t can be multiplied by a number, and then it can be added to itself. And so I created a concept for that, and then we're just going to do that same, we're going to constrain everything down below as well. Cool. So let's look at our compiler error output. I'll give everyone a minute to read it. So if you notice here, it's pointing directly at what the error is, and it's super easy to read. You could give this to someone who it's their first week writing C++, and they'll know exactly how to fix it and exactly how to deal with the issue. This is something that you'll be able to understand exactly, and you aren't going to end up spending as much time trying to diagnose your errors. Which, if you think about it, that's increasing your productivity time and allowing you to write a lot better of code. So this is something that's of net benefit and makes it so that way we know exactly what we're doing and how to make things better. However, the one big con is that you do have to get up to C++20 to really start being able to write these. So SFIN has hard to read error message, and it's really difficult to make some of those complicated checks. In that case, sometimes one of a better option would be using a static assert inside of it, so that way you can static assert at compile time and kind of label, here's why this is failing. Because then you're going to have something nice to read, and it's going to be a lot easier. And then concepts, they replace spin-A, and they have those easy-to-read error messages, however, they are in C++20. So this is definitely one where the newer thing is better than the old. However, since many people aren't running the newer thing, you are unfortunately stuck with the old. Cool. And then now we're going to look at polymorphism. Cool. So I worked in a code base that had a ton of polymorphism and did a lot of the more object-oriented design. And one of the things that I noticed is that there's times when you want to kind of move things up and have other classes share with what you're doing. And so basically what I wanted to do is take and implement don't repeat yourself and be able to have this base network connection that has some of these functions that I want to call and some of these generic things that are called every single time, and have two derived classes, my TCP and my UDP. And that's something that you see a lot depending on a lot of networking as well as a bunch of other implementations. Cool. So kind of our timeline, we have our virtual functions, which have been around for a really long period of time. And then we have the curiously recurring template parameter, or template pattern, which is CRTP. And then we have deducing this, which is the C++23 feature. So only a couple of you are going to have access to it so far, but it's one of those to keep in mind when you end up moving to C++23. So virtual functions, they're runtime polymorphism, and they're kind of quintessentially overused. If you talk to someone, they tend to say, okay, well, we've used virtual functions so much, and part of that's because you do have things such as the vtable, which gets a really bad rap. And so there are things where it's like, I really need this runtime polymorphism, but then there are a lot of things where we end up not needing it as well. Cool. So here's kind of our example here. We have initialize config, which is a pure virtual function, and then inside of init, we're going to call initialize config. And because it's a pure virtual function, we have to have a child of this class. And so we have our TCP and UDP childs that will implement initialize config, so that way they can be called whenever you call init, and it can add additional logic as needed. Cool. And then we have our curiously recurring template pattern. So this is compile time polymorphism, and it basically forces a downcast from the parent to access the child elements. Who here has used CRTP? Okay, we're getting a decent chunk of hands. Cool. And then it's very explicit, and you can see that explicit cast. Now jumping back to the previous one of the nice things about it is we do have our virtual and override. So we have these keywords that we can look at inside of our class and know exactly what's going on. We see, okay, virtual, okay, we know that this is probably being overridden somewhere else. And then we see the override and we know, okay, this is overriding something that's in a parent class. And so this is super visual and super helpful for us writing code and reading code, because it's taking away that visual impact on the reader and allowing us to understand what's going on without actually having to think about it. Cool. So now we're going to look at some CRTP code. Cool. So I'm going to give everyone a minute to take a look at that. So with this, we're going to have our base class templatized on the derived class, and then all of our derives are going to inherit off of the parent class with the template type being itself. And with that comes some potential issues of if you accidentally put in the wrong type, you could have the CRTP can end up accidentally falling apart and can lead to some really weird bugs that can be kind of hard for us to diagnose and understand what's going on. However, it can be really nice and it can be really creative and allows us to do a lot of things. And so the static class allows us to call the child's initialize config from the parent class. And this is done because the parent object, the initial, Cool. And then next is implicit object parameters, or deducing this. Now, who here has heard a little bit about deducing this? Okay, we got some hands. Cool. So this is a C++23 feature, and it simplifies some of the compile time polymorphism. If you've looked at the paper for deducing this, it does talk a little bit about how it can end up replacing some of the instances of CRTP, and we're going to look a little bit into that right now and figure out, is it doing things a little bit better for this virtual polymorphism, or is it not? And they're both compile times, so this is nice because when we're running into issues where we really aren't dealing with the runtime polymorphism and we don't need the runtime thing, we just want to move some of our implementation details up into some parent class, this can be really beneficial. Cool. So here's our deducing this code. And as you notice, we have this, this auto ampersand Anderson self, which allows us to access the element the class that we called from. So although this is the parent, if it's called from the child, it's going to access the child. This is the child that we're going to access. So it's like the child dot initialize config is how we're going to actually end up accessing that element. And so that's how we're able to access the initialize config from either one of the children. Now, if you notice, this cleaned up a lot compared to the CRTP. So if we go back to the CRTP, we have this static cast, which is definitely a lot of characters, and it can be a little bit harder to read. And you also don't have all the templates that are going throughout, and so you don't have to worry about making sure you're doing those templates correctly. Yeah, so it does clean things up a good bit, but it's also one of those of, if you don't know that this feature exists and you accidentally run into it, it can be really confusing and really hard to read and understand. Cool. So now we're going to look a little bit at multi-level inheritance. So first, we're going to do virtual. We're going to use that runtime polymorphism and look at trying to do virtual inheritance. And so what we're going to do is I have a couple of different examples, and we're going to try and predict what's going to be outputted from our main. So the first one's our multi-level inheritance. So I'll give everyone a chance to figure out what A.init and B.init end up outputting. Cool. Can I get like thumbs ups when everyone's figured out what their answer is going to be? Cool. And I'm not trying to play any sneaky games here. This is all like, I'm not playing any hints, so it should be pretty simple. Cool. Starting to get some thumbs ups. Awesome sauce. Okay. So the answer is TCP and session. So as you could assume, the session is inheriting, and through that inheritance, we're going to end up calling, and we're going to get session out, and then we're going to get TCP out for the other one. Or sorry, yeah, we're going to get TCP out for the first one and session out for the second one. And so we have network connection, and then TCP inherits from network connection, and then session inherits from TCP, which inherits from network connection. And so since that is our lowest level object, we are going to get that out as expected. Next, we're going to look at multi-level inheritance using CRTP. So I'm going to give everyone a minute, give a thumbs up when you figured out what's going to be outputted here. We're starting to get some thumbs ups. Cool. So I'm going to ask this time, who thinks TCP-A, the first one, is going to output TCP? Cool. Who thinks it's going to output session for the first one? Okay. And then for the session, or B.init, who thinks that it's going to output TCP? And then who thinks it's going to output session? Cool. So actually both output TCP. And this is because doing the multi-level inheritance with CRTP can be really difficult. It's one of those, so we have if we look at our code, first we have our template class derived, and then in our next class that ideally would inherit from it compile time, it's also templatized because we need to do like multi-level CRTP. And so this one's also templatized, but then it's also instantiating the template of TCP in the network connection. And then session is calling with TCP with a specialization of session. However, the template for the TCP class isn't doing any sort of specialization to kind of direct that that it's getting passed in up to the next level. So network connection has no idea that TCP or that session or that session was that TCP was templatized on session. It just doesn't see that because it's not being passed up another level. And so this is one of those where it's not quite intuitive, and because we're dealing with all these passing template parameters, it can get really confusing really quick. And something like this is something where it's like, maybe I'm wanting to do this multi-level inheritance, and I'm not going to expect it to do the thing that I would think it does. Cool. And with this, you notice that because we're moving to this compile time, we're only calling off of the lowest child object. So we aren't calling it off of a higher level object, which is something that Klaus talks about in his talk earlier this week, is how there can be some issues, especially with deducing this, of trying to call it from the top level object. So I'd look into that just as you're trying to understand a little bit more about how deducing this is ending up working, and so that way you aren't going to run into some common pitfalls when looking at your code. So this is deducing this. I'll give everyone a minute to figure out kind of what they would expect. Cool. Can I get some thumbs up as people figure it out? Cool. So most everyone's figured it out. So who thinks the TCP outputs TCP? Can I get a hand raise? Cool. Who thinks session is outputting TCP? Okay. Who thinks session is outputting session? Cool. So everyone pretty much raised their hand for it and got it. So the cool thing is that because deducing this is looking at the pointer of that object that you're calling it from, it's going to know that initialize config is being called from that lowest level object. And this is a lot easier than CRTP when we were trying to deal with all those templates for this multi-level inheritance structure that we've created. Cool. Who thinks this is kind of neat? Cool. We got some hands. Cool. So here's kind of our comparison of all three of these alternatives. So virtual polymorphism's really nice because it's really easy to track, really easy to understand, and it's really natural. And part of that comes from the fact that we're taught. So who here was taught using more of an object-oriented model when they initially learned? Okay, that's pretty much every single hand. So if you were to imagine that instead of being taught in more of this object-oriented runtime polymorphism model, that we were taught instead using something like compile time polymorphism, some of this stuff would probably feel a lot more natural. And that's just because we aren't used to it, and this is something that we're still learning. This is something that isn't natural to us because we haven't done it a lot. However, who here likes seeing that virtual and override and uses that kind of as a context clue when they're looking at code? Okay, basically everyone. So this is one of the really nice things about it, is it's super easy to read, super easy to understand, and if we're looking at that longevity of a code base and trying to understand how to quickly look at code, this is a really great way to do it and enables us to look at code very quickly. With CRTP, it's compile time polymorphism, and it can be a little bit harder to read. It's also a little bit visually obvious, like less visually obvious what we're doing. So if you look at CRTP for the first time, you're going to end up taking a step back and not knowing what's going on and having to make sure everyone understands what's going on, which can be a really big hindrance in code bases where you end up having a lot of junior engineers because you spend a lot of time trying to educate people on here's what CRTP is and here's how CRTP works, and having to make sure that no one's making mistakes on which parameter is going in where and what's being templatized on, and making sure that that the derived is called correctly, and making sure all these things end up working correctly. So if we have that happen, then we can end up running into some weird bugs that we aren't expecting and having to keep an eye out for some additional things as a programmer. However, it does allow us to do compile time polymorphism, which is a really big advantage, especially performance-wise. It also does have some difficulties with doing some of the multi-level inheritance, which can make it a little bit less appealing if you're trying to do some really complex things. However, the question becomes, is this something we should be doing, or is this something that we're kind of over creating objects? We're making more difficult situations than we need to be making, and we're overcomplicating the situation. And then we have deducing this, and that's compile time polymorphism. However, it's in C++23, so most people aren't going to have access to it, and most people aren't going to know about it. And it also obscures the code. If you look at it, you aren't going to know that you're doing all this interesting calling up above unless you see it and you're looking at that base class. You won't know that this is happening unless you look at the base class. Otherwise, you aren't going to know, like, oh, this is actually referencing and being called from there, and that it's actually going to pull from the lower level class and calling its child. We won't know that. And so we need to make sure that that's communicated, and that may take more time to actually go dig through your code than looking at runtime polymorphism or looking at CRTP, where CRTP, it's immediately obvious we're playing some games and we're going to do something in the parent object via those templates with the derived, because the standard is that we have derived as that name. So we're going to know immediately what games we're playing and where we need to look. And deducing this kind of covers it up and makes it a lot cleaner, but makes it a lot harder to visually understand what's going on. So that can make it a little bit more difficult. So now let's look at some other evaluations now that we've kind of evaluated a bunch of the different alternatives that we have and are trying to figure out exactly like what's good, what's bad. And so that way when we go back home and we go look at our own code bases, we know exactly what things we need to look for, and so we can do our evaluations on our own and understand what's going on. So the first one is union versus variant. This is one that's probably a little bit more obvious since we've had this discussion across multiple years about what the pros are of variant compared to union. However, it's nice to do that refresher and have those really obvious ones where newer is probably better than the older alternative. Next is enum versus enum class. This is one that you still see a lot today, even though we've talked about how enum class allows for additional type safety and additional help. And this has been helped a lot with things like C++'s 23's to underlying, making it a lot easier to access the underlying type when we need to access it. Next up is raw pointers versus reference versus smart pointers. So understanding kind of when we need to use it, as well as what are the pros and cons of each of these, and understanding what's good and what's bad, so that way we can end up making a more informed decision when we're writing code and not just, let's say, generically use smart pointers everywhere where we may not need them, or be using raw pointers across our entire code base just because it's something that we think we need to do and we haven't migrated to even looking at smart pointers yet. Up next is raw iterators versus some of the standard algorithms, kind of understanding like what are the pros of the standard algorithms and what are the cons and what are the pros and cons of some of the iterators. And then next is C-style casts versus fancy casts, as I like to call them. So those are your static, dynamic, reinterpret, and const casts. So understanding is there pros and cons to the C-style cast versus some of these fancy casts, and like where can we be using each of these and where should we be using each of these and what are the pros and cons of each. And then next is allocators versus PMR. And then printf versus CAP versus lib format. So kind of looking at kind of which one's better and why is each one better in which use cases. And then the next one is object-oriented programming versus functional programming versus data-oriented design. And I think with a lot of these, you look at it and you realize you can't just do one. Like one of these design trends isn't the answer for everything. It's just a tool in our toolbox. And our goal as software engineers is to have the largest toolbox possible, so that way we can intelligently pull from the right things. We aren't just pulling out the brand new screwdriver that we bought a week ago because it's cool, it's shiny, and it maybe has this really cool feature and looks cool. Maybe we actually need the tool that's been sitting there for a long period of time because it's reliable and it works and it fits this use case and identically matches. But we can't use either one of those tools for every application and for every use case. As well as we may have the tool that's basically broken or has been completely superseded by something else. And so we need to be able to look at that and understand which one we should be choosing for what. So in conclusion, newer isn't always better. And that's kind of the idea of we need to take 5 steps back and evaluate what's going on in order to write good code and in order to deal with what issues we have in software engineering and to be able to write the best software for the future. And consistently reevaluate alternatives. I think kind of the goal is that we don't stop learning, and we learn that from coming here. If we don't stop learning and keep investigating new trends and old trends, then we'll be able to write better code in the future and know here's when we need the old trend and here's when we need the new trend. And then use case determines usability. So for one use case, we may want to use the older style thing because this is where it works and this is where it thrives. And in another use case, maybe we want to use the newer thing because it allows for this thing to be simplified massively. And so we need to figure out which ones of those there are, as well as figure out when is it time to migrate from an old thing to a new thing, and when is it time to just keep the old thing because we know it works and we have that legacy heritage, and maybe it's not worth the time and the cost in order to upgrade. So yeah, thank you so much. Are there any questions?
Hi, thanks very much for your clear presentation of this pragmatic and useful material.
Thank you.
I was glad you mentioned Klaus's talk as well. It goes into CRTP in some detail, so it's a great complement to this talk, and I definitely recommend it to the YouTube viewers of the future. I did have a question about the multi-level CRTP example.
Okay.
Klaus in his talk mentions 2 different ways to use CRTP. Like sometimes it's used as a mix-in for like adding functionality to a class, and sometimes, and this was new to me, but we were using it as a kind of like static polymorphism alternative. And I've never seen, when I saw your example, I realized I've never seen a multi-level hierarchy with CRTP. So like, A, I guess, is that a thing that people do? I haven't seen it before. And B, could you clarify, like, was this example intended to be more of a mix-in style or a static polymorphism style? Thanks.
Yeah, so this is definitely kind of in between. So I've actually never seen something like this done in industry, but it's one of those that like I've written a lot of previously, like using that virtual polymorphism code in order to abstract away some of these behaviors that we have. And I'm like, I don't want to deal with the V table because all this is compile time. I don't need runtime type information. And I'm like, well, what if we move it to compile time? And so since we are doing that single level, I was like, what happens if we do multi-level, and where does that get weird? And so that's kind of how I ended up falling into this example. And since you're right there, do you have an opinion about if it's mix-ins or polymorphism? It feels like static polymorphism, but I'm not accessing the top element ever.
Microphone?
Yeah, sorry.
So you do your session directly. So you don't really use the interface, but yet you have multiple inheritance. So you kind of replace the initialize config function somehow. So it's really some kind of in-between case.
You know, when I look at it now, like in light of your explanation, I feel like you helped me like answer my question. I think that this example is maybe a trap for the unwary, people who come from virtual polymorphism, and they want to just take what they have and migrate it over. This is you coming out here and saying, hey, if you try to do that, it could get really weird. And instead of doing this, you should go watch Klaus's talk and like get clear on what you're actually intending to do.
Thanks. And just to summarize, I did say that the explicit object parameters are much cleaner in this case, and you kind of proved the point.
Okay, thank you. Yeah. And so that's one where if you are trying to do the multi-level, move over to deducing this, and it'll probably look a lot nicer. Cool. Are there any other questions? Okay, awesome. Thank you so much.